So let me say x1 of t is one signal which has a Laplace transform, unilateral Laplace transform as x1 of s. So let me say if x1 of t has a Laplace transform x1 of s, and similarly x2 of t has Laplace transform x2 of s, then what is the Laplace transform of x1 of t convolution x2 of t. Let's also assume that assume x1 of t and x2 of t are causal signal. Okay, so causal signals, I hope you know what it means. It means that is value of these functions is 0 for t less than 0. So that's what we mean by causal signal. Okay, not causal system, we are talking about signals here. So x1 of t has a Laplace transform x1 of s, and x2 of t has a Laplace transform x2 of s. Then what is the Laplace transform of convolution of these two signals? Okay, so let's look at what happens. Laplace transform of x1 of t convolution x2 of t. If you do this, then integral convolution Laplace transform formula is t going from 0 minus to infinity x1 of t convolution x2 of t into e raised to minus st dt. So this is the formula. Now what I will do, I will substitute. So t going from 0 minus to infinity, I will substitute the definition of convolution, which is what is the definition of convolution? It is minus infinity to plus infinity, first function in terms of tau into x2 of t minus tau d tau. So this is the way we have defined convolution. Okay, into e raised to minus st dt. Now we have said that these functions are causal signals. These signals are causal signals. So therefore we know that x1 of t for t tau less than 0, it is going to be 0. So what we can do is that we can change the limit from minus infinity to 0 minus. We will not make any error because x1 of tau is 0 by definition, but it is given in the problem itself that so we can put it like 0 minus to plus infinity. That limit on tau we can put it like that. So let us put that. So integral t going from 0 minus to infinity. So I am putting tau going from 0 minus to plus infinity, x1 of tau, x2 of t minus tau d tau into e raised to minus st dt. So now what I am going to do is, like, I am going to interchange these integrals. that is tau integral. According to this expression, we are doing it for the first time. We are doing tau integration, and then whatever we get out of it, we are doing the t integration. Now let's interchange this tau integration and t integration. So we will do t integration first. So if we do like that, so I will write tau going from 0 minus to plus infinity. So whatever is only a function of tau, I can take outside, that is x1 of tau, and then I can keep all other terms inside. So t going from 0 minus to plus infinity, there is x2 of t minus tau, because t is there, and then e raised to minus t, there also t is there, and then dt. So this one I will put it in bracket now, and then outside I will have a d tau. Now if you look at what is inside this bracket, so what is inside this bracket, there is t minus tau here, and if we can bring t minus tau in this expression, and if you do a variable transformation, so let us do a variable transformation. Let t minus tau is equal to u, let's put, and then we can say that dt is going to be equal to du, because with respect to the t integration, t is the integration variable, tau is a constant. So during the t integration, so dt is du, because that is a new variable. And another thing is that okay, so we also need to change this integration limits. So when t goes to 0 minus, then what happens to u? So u is basically u, and t is so what is u? U is t minus tau, so u is equal to minus tau, and then when t equal to plus infinity, we will have u is equal to, so t is plus infinity, u is also plus infinity. So we will have the same limit for upper limit, but lower limit we will have u going from minus tau to minus tau onwards. Okay, so this way if you change the variables, so we can write it as integral tau going from 0 minus to plus infinity x1 of tau into integral. So now integration is with respect to u goes from minus tau to plus infinity x1 of u into e raised to minus s, and t is what? U plus tau. Okay, so if this is the definition of u, so t is from this expression, it is u plus tau, and then we have du, dt is same as du, so we can put that, and this is the first integration. So we are now doing u integration first, and then d tau. Okay, so that is what we are getting, and that's equal to integral. So there is a term e raised to minus s tau, which is something that is independent of u. We can take it outside. So tau going from 0 minus to plus infinity, and you can write it as x1 of tau, and the other term I am taking it outside, that is e raised to minus s tau, and then in the bracket I have integral u going from minus tau to plus infinity. To be more exact, it will be tau minus. Okay, this will be tau minus. This one also be tau minus. Okay, so that is that will matter only if there is an impulse or something like that at that starting location or tau. Otherwise, even if you don't put it, it's okay. So let's okay. So what we have is like x1 of u into e raised to minus su du into d tau. So this is what we have. So we are integrating x1 from minus tau to plus infinity, and we already said that this function x1 of u it doesn't have any value in the negative values of argument. Okay, we already said that. So we know that x1 of u is equal to 0 for or if you say variable as u, then u less than 0, and it is x1 of u for u greater than or equal to 0. So therefore this limit, though we have put it as minus tau or minus tau minus whatever, it doesn't make any difference in changing that to 0. Okay, so let me rewrite it. Tau going from 0 minus to plus infinity, x1 of tau into e raised to minus s tau into this bracket. I can again put this as 0 minus. So 0 minus, I am bringing it back. The reason is that x1 of u is 0 for u less than 0. Okay, so we don't need to integrate. I am assuming tau as positive. Okay, so I don't need to integrate from negative values of time. I can start from 0 minus because that is where it matters. So this is x1 of u e raised to minus su du. Now this one is nothing but the Laplace transform of unilateral Laplace transform of x1 of u, and we have called it as x1 of s, and therefore we can write it as, so x1 of s I can take it outside. I think somewhere I have okay, so this should be x2. Okay, this is x2, here also x2. Okay, that was a mistake. Okay, so x2, this is x2 we are talking about, and x1 is here. All right, so now let's so what is this equal to? So this is equal to, so we are looking at unilateral Laplace transform of x1 of t convolution x2 of t. That's what we are doing, and what we got it as integral 0 minus to plus infinity. So the integration that we are left to do is I think the tau integration. We have x1 of tau into e raised to minus s tau, and then the bracket I said it is x2 of s, so d tau. Now x2 of s is a constant in the tau integration. So tau is varying from 0 minus to plus infinity. So x2 of s, I am taking it outside, and the remaining thing, if I am writing, then this is in a standard form, which is basically the Laplace transform of this is x1 of s. So therefore what we get finally is x1 of s into x2 of s. So this is a very important property, that is, like when you convolve two signals x1 of t and x2 of t and then take the Laplace transform, it is equivalent to just multiplying their individual Laplace transform. Okay, the convolution result, okay, Laplace transform of the convolution result is the the product of the individual Laplace transform. So if you know the Laplace transform separately of x1 of t and x2 of t, only condition is that they are causal signals. So these causal signals only you can talk about this way. This property is valid only for causal signals. If it was not a causal signal, then what would have happened is that we would not be able to write this like this. Okay, this minus tau limit we cannot make it 0. So the reason why we are able to do that is because this x1 of t as well as x2 of t, they were 0 for the argument less than 0. For negative values of the argument, its value is 0. So that is what we mean by causal signal. In the case of causal signals, the Laplace transform, unilateral Laplace transform of the convolution of two signal is equal to the product of their individual Laplace transform. So this is a very useful property. Now this property exists perfectly well for bilateral Laplace transform. That is, if the limit of the Laplace transform formula is from minus infinity to plus infinity, then we don't have any restriction that the signal has to be causal. Okay, we can have any signal and this property will be valid, but that is for bilateral Laplace transform. But in this course we are focusing more on the unilateral Laplace transform. The reason is that that way we can find out zero state and zero input response categorically, and this is what matters for practical purpose in solving the response, solving for the response of the systems. So I hope it is clear. So if you have any explanation further required, let me know, otherwise I'll move on. Okay, so now if that is clear, let us come back to the problem that we were doing yesterday, that is like Laplace transform of integral integral 0 minus 2 t x of tau deta. So this let's now come at this problem again. So this is a problem that we did yesterday. Okay, yesterday what we did was like from minus infinity to t x of tau deta. So find this given, find this given that x of t say Laplace transform x of s. Okay, so it is not x2 of t, just x of t. X of t has a Laplace transform x of s. If that is the case, then find the Laplace transform of the integral of x of tau from 0 to t. So yesterday we did it in a different approach, but now today let us solve this problem in a slightly different way. So now what I would like to argue here is that I can write this given integral, that is this 0 to t x of tau deta. I can write it as a convolution of x of t and u of t. I can write it as a convolution of x of t and u of t. So let's see whether this is true or not. So let's apply the formula for convolution. So is it correct? So now we have not shown that it is true, but now let's check whether it is true. So let me just write it as a separate line. Okay, so x of t convolution u of t. What do we mean by that? So this is our RHS. What we mean by that is like for the case that we are considering. Okay, so let's also say that x of t is equal to 0 for t less than 0. Causal signal again for t less than 0. So if that is the case, I can write so tau going from minus infinity to plus infinity, that is the original formula, and then x of tau into okay, let me we have already proved that convolution okay, let it be this way. Okay, so this is equal to tau going from minus infinity to plus infinity, x of tau into u of t minus tau. I just applied the definition of this convolution. Okay, first function in terms of tau into second function, the argument is replaced by t minus tau. So that's the formula. And since u of t is also, by definition of u of t, it is also 0 for t less than or equal to 0. So both functions are causal signals in this case. Okay, u of t is already causal, but we have insisted that x of t is also causal, so that the earlier property remains valid. And in that case, what we can do is that I can write this integration as tau going from 0 to 0 or 0 minus to t x of tau u of t minus tau. So if tau is smaller than t, if tau is smaller than t, so u of t minus tau is positive, the argument is positive, and it is going to be equal to 1, and therefore it is this. So this is what we started with. So this is our LHS. Okay, so you can see that this is our LHS. Is that clear? So we started with the RHS and then applied the definition of the convolution integral, and then since u of t and x of t are causal signals, u of t is already, by definition we know that it is causal signal, x of t we are taking a particular signal which is causal. Okay, x of t is a signal, it is valid only for causal signal. Okay, so we are saying it is 0, and then what we are finding out is that the limit can be changed. The upper limit is t and lower limit is 0 because x of t is causal, and the upper limit is t because u of t is causal. Okay, so t minus tau, if tau is lesser than t, then t minus tau is positive. At that time it is equal to 1, but if it is t is less than tau, then the argument is negative and it is going to be 0. So that is why we are integrating only up to t where it is 1. So that is our LHS. So therefore we can now say that the problem that we wanted to solve, that is this Laplace transform of the integral, you can also write it as a unilateral Laplace transform of x of t convolution u of t. You can also say that it is this. Now we derived a formula that so if this is the case, then you can write it as Laplace transform of x of t into, now it is product, into Laplace transform of u of t. So therefore if you know the individual Laplace transform, then you take the product of it, and that will give you the result. So now what is the Laplace transform of x of t? That we know that it is x of s. It is given in the question that the function has a Laplace transform. Okay, so this one, the function has a Laplace transform x of s. So that is given, and we have already found out Laplace transform of unit step function. It is 1 by s. So this is equal to x of s by s. So this is what yesterday also we got in another way. So this is a different way of arriving at the result. So yesterday what we did, let me repeat it again. Alternate way was we have integral 0 minus 2t x of tau d tau. And we said that it is equal to some different function, say y of t. So this is let us let this is equal to this, and then what we did was like, and also we insisted that x of t is equal to 0 for t less than 0. So this is what, so that is, the signal is causal, and we, whatever we integrate and get, that we call it as a different function y of t. And therefore if that is the case, then if I take a differentiation on both sides, I will get basically this is basically x of t is equal to y of so dy by dt. Okay, so you integrate it, you will get x of t, or maybe I should write dy by dt is equal to, so therefore dy by dt, we call it as x of t. That's what we did, right? And then what we said is that Laplace transform of this on both sides, if you do dy by dt, then that is equal to Laplace transform of x of t. But this we know, this is x of s, right? This we know that it is equal to x of s. And we also know that the property of derivative of a Laplace transform, that also we know. So that is Laplace transform of dy by dt, this is equal to x of s. Okay, so now what is the Laplace transform of this? So this is basically s y of s into or minus y of 0 minus, right? That is a formula for finding the Laplace, and that is equal to x of s. Now what is y of 0 minus? Y of 0 minus is equal to, according to the definition, we have 0 minus to t, so t is equal to 0 minus x of tau d tau. So there is no integration here, basically upper limit and lower limit are same. In that case this is equal to 0. So this is basically equal to 0, and therefore y of s is equal to x of s by s. So this is what we did yesterday, and we got this same answer. Similarly, you can do this in this manner also by using the property of convolution. Okay? There are two alternate way, two methods to find the same function. Okay, any questions? No questions. Okay, so let's look at some of the left out things. Another thing that I want to do is given, okay, so given x of t has a Laplace transform x of s, find the unilateral Laplace transform of t x of t. What is the Laplace transform of t x of t? Okay, so how do we do this? So one way is like you just start from what is given to us. So that is what is given to us is x of s is equal to integral x of t, t going from 0 minus to infinity, e raised to minus st dt. This is what is given to us. That's by definition of x of s. That is how we find the Laplace transform of x of t. Now what we want to find out is what we want is basically Laplace transform of this, and Laplace transform of t x of t, if you look at, so that is basically equal to integral t going from 0 minus to plus infinity t x of t into e raised to minus st dt. Now, so let's call this as equation 1 and this is equation 2. If you compare the two equations, the only difference is that there is a t. Now, starting from equation 1, how can we arrive at the RHS of the right hand side? One simple method is that if you take a derivative of the first equation with respect to s on both sides, then the t will come out, right, and it will begin to look like this. Okay, so that is the approach that we will take to solve this particular problem. Okay, so taking derivative with respect to s on both sides of equation 1, what we get is dx of s. This is a function of s, so we can take a derivative with respect to s. So dx of s by ds, so that is equal to integral t going from 0 minus. So since s is constant with respect to t, I can take it inside this integration. The only function that is going to have s dependency is e raised to minus st, and this is dt. Now this this derivative is very simple. That is, derivative of an exponential is whatever is the coefficient in the exponent, that will come out. Now if you consider it as a function of s, the coefficient is minus t, so that will come out. So minus t integral t go from 0 minus to plus infinity x of t into minus t into e raised to minus st dt. So now you see that it is almost looking like equation 2, so except for the minus sign. So therefore, if you take the minus sign or divide both sides by minus 1, so what we will get is like therefore integral t going from minus infinity 0 to infinity. So I can write it as tx of t and e raised to minus st, and what is it equal to? This is equal to minus dx of s by ds. This is a very useful property to extend some of the results that we have already obtained to cover functions which is multiplied with t. For example, given that x of t is equal to say e raised to minus at, e raised to minus at u of t. Okay, and we know that taking Laplace transform, we know the value of x of s. So this is a problem which uses the above property. So x of s is what? 1 by s plus a, that is known to us. So then we can easily find the Laplace transform, okay, Laplace transform of t into e raised to minus at u of t. So this we can easily find out. What is it? This is equal to minus d by ds of x of s, which is minus d by ds of 1 by s plus a. Okay, and now what is this derivative? So this derivative, if you find out, so this is equal to we can write it as d by ds minus of s plus a raised to minus 1. So when you take the derivative, what will happen? Already there is a minus 1 here, and when you take the derivative, another minus 1 n and then s plus a all raised to minus 2. So that's the derivative, and minus 1 into minus 1 is 1, and this is basically 1 by s plus a the whole square. So this way you can find out these results. This we can find out alternatively. Another method also is there. So if you know what is the derivative of also we can say also we know an alternate approach. Okay, also we know that t u of t has a Laplace transform. Okay, Laplace transform 1 by s square. So this we have earlier derived in one of the earlier class, and then when you multiply, so this is x of t if you take, then this is our x of s. So if x of s has a Laplace transform x of s, then e raised to minus at x of t will have Laplace transform where s is replaced with s this is replaced with the x plus a. Okay. So this is another property. Okay. This way also, which is basically 1 by s plus a whole square. So you can use this property also to find out. So either multiplication by t you can use, then you should know the Laplace transform of the remaining part of the term, that is e raised to minus at x of t, u of t. If you know that, then multiplication with t you can by taking the derivative, or if you know t u of t as 1 by s square, then multiplication with e raised to minus at will basically result in changing s to s plus a. We have proved also this result earlier. Okay, so whatever is the approach you take, you can get the result in multiple ways. Okay, and in the remaining part of the time, I would like to discuss two important theorem. One is called initial value theorem. Initial value theorem. Okay. So initial value theorem says that if you are given the Laplace transform of some function, so given the Laplace transform, again we are only talking about unilateral. Given the Laplace transform of a function, how we can find the initial value. Okay, initial value. So the function x of t is Laplace transform is given, then the initial value means 0 plus. This is what we mean by initial value. Okay, so this is our initial value. So the function is given as this x of t. Its Laplace transform is given. The function is not given. If the function is given, then just put t equal to 0 plus, and you know the initial value. But the function is not given. Only the Laplace transform of the function is given. So directly, so there are two ways you can find out x of 0 plus. The straightforward method is like, so if x of t is given, then you can find out, x of s is given. So if x of s is given, then x of t you can find out as step 1. This is straightforward approach, that is Laplace transform inverse of x of s. And then step 2 is, after finding out this, you can just put t is equal to 0 plus and find x of 0 plus. So this is one direct approach. You just need to do 2 steps. Step 1, you have to find the inverse, but inverse finding, it takes some work, right? Usually from you have to expand it in terms of partial fraction. It may result in complex conjugate root, or it may result in multiple terms in the numerator, and then you have to expand it, find the residues, and then taking the inverse of the standard terms, and then finally put t equal to 0 plus, and that is your initial value. But this theorem called initial value theorem bypasses all of this. You can directly find out what is initial value from the x of s itself. So this is given. So from x of s directly how we can find the initial value x of 0 plus, small x of 0 plus. So the method is like this. So we use this property. So the proof or the derivation. So learn this derivation. It's very easy. So we know that unilateral Laplace transform of dx by dt. What is it? This is s into x of s minus x of 0 minus. Okay. So therefore s into x of s minus x of 0 minus is equal to, what is it equal to? If I apply the definition of this, that is 0 minus to infinity, dx by dt e raised to minus st dt. Basically, we just, in order to prove our initial value or derive our initial value theorem, we just need to start from this property of derivative of a function, Laplace transform of the derivative of a function. Okay, so this is equal to this. Now what we are going to do, the next step is just write it as, we need to bring 0 plus into the scene. So 0 minus to 0 plus, I am just splitting this integral into two parts, which I can do, and then plus 0 plus to infinity dx by dt e raised to minus st dt. Okay, so this is what we have. Now if you look at the first part, this is actually integration from 0 minus to 0 plus t is equal to 0, and therefore I can write it more appropriately as just dx by dt. Yeah, and e raised to, anyhow t is 0, so e raised to 0 is 1, so I can write like this, and this term as before. Okay, now if you look at this is basically integral of the derivative. What does it mean? It means like x of 0 plus minus x of 0 minus. Okay, and what is this? This side it is s x of s minus x of 0 minus. So plus this term into e raised to minus st dt. Now you see direct these two you can cancel. Now you have almost x of 0 plus. So we brought this x of 0 plus here. That's what we wanted. But it is equal to s into x of s, and there is one term here. And if we can make this term vanish, and the way we can make this term vanish is that if you put s, if you take a limit where s goes to infinity, then e raised to minus st, e raised to minus infinity, we know that it, so in the limit taking the limit s goes to infinity, s goes to plus infinity. So if it s is going to plus infinity, e raised to minus st is going to become so that e raised to minus so that e raised to minus infinity into t goes to, or you can say e raised to minus st goes to 0. So that means this term will go to 0. So therefore limit s tends to infinity, s into x of s is equal to x of 0 plus. So this is what we call as the initial value theorem. Now you look at this expression. What does it say? It says that given x of s, I can find out the initial value. What I need to do? Just multiply the given x of s with s and then take the limit s goes to infinity. That's all what we need to do. Okay, so similarly there is another alternate theorem which is called as the final value theorem. So earlier was initial value theorem. Final value theorem. So what is final value theorem? That means given, what is given? Given x of s, which is the unilateral Laplace transform of x of t, find x of infinity. So that is a problem. So again we can do this in two steps as before in a straightforward method. If somehow you forgot about final value theorem, then also you can do this. What you need to do? Find x of t, which is the Laplace transform inverse of x of s. X of s is what is given. So you find the inverse. So that will require partial fraction expansion and all. You find it, and then that is step 2, step 1, and then step 2. What you can do is put t is equal to plus infinity to get x of infinity. So that is a straightforward method. Okay, so this is the direct method. But now we want to bypass all this inverse finding, and you can find out. So what final value theorem says is that if x of s is given, multiply, just like before in the case of initial value theorem, we multiply this, but now you take the limit s going to 0. So this is your final value. Okay, so this is what the final value theorem is. So final value can be found out. Multiply the given x of s with s and take the limit s goes to 0. Alright, so if you want to find or proof, let's say proof, just like we did the derivation for the other. Again, this derivation also starts with the same property, that is s into x of s minus x of 0 minus is equal to integral t going from 0 minus to plus infinity dx by dt into e raised to minus st dt. Again we are starting with this property, that is the Laplace transform of the derivative of x of s is already derived earlier. Using the integration by parts method, we obtain this result. Okay, so we take that result, and then what we are going to do is we are going to do a manipulation. This time the manipulation that we are going to do is like taking the limit directly, s goes to 0. So what will happen to RHS? Taking the limit so x goes to 0, we get e raised to minus st goes to 1, right? S goes to 0. Earlier we said s goes to plus infinity. In that case this term will become 0, but now s is going to 0, so e raised to minus st become 1. So which means x into x of s, and now there is a limit. So let me write the limit s tends to 0, s into x of s and limit will not do anything with for x of 0 minus, because there is no s in it. On the other side, when you take the limit, as I said, it goes to 1. E raised to 0 is 1. So this is t going from 0 minus to plus infinity dx by dt into 1 dt. Now if you look at this RHS term, I can you see integral of the derivative. Integral of the derivative is x of t with limit 0 minus and plus infinity. So that is limit s tends to 0, s into x of s minus x of 0 minus is equal to x of infinity minus x of 0 minus. So you see that these two terms you can cancel. They are not 0, they are cancelled. From both sides we have that term. So that's it. We have arrived at the result that we wanted to prove. So that is x of infinity, or the final value. Okay, that is what we mean by final value. S tends to 0, s x of s. So you see that the two properties are very similar. Okay, if you want the final value, you multiply x of s with s and then take the limit s goes to 0. If you want the initial value, what we need to do, multiply with s, but take the limit going to s going to infinity. So you can do problems with this. Let's say problems. So given x of s is equal to s plus 2 by s into s square plus 2s plus 3. Find x of 0 plus, that is the initial value, and the final value. So let's see what happens. So first let us find out what is the final value, or whatever. So x of 0 plus, okay, so this is the initial value. Is equal to limit s tends to infinity, s into x of s. So that is limit s tends to infinity. When I multiply the given x of s with s, it will become s plus 2 divided by s square plus 2s plus 3. Okay, s got cancelled. Now to find the limit of s going to infinity, it is convenient to take s outside. Yeah, take s outside, and you can, okay, so let me write it as limit s tends to infinity. Let's take s outside, and that will become 1 plus 2 by s. And then here also, if I take s outside, so that will be s plus 2 by s plus, sorry, s plus 2, s plus 2 plus 3 by s. So this s will cancel. Now if I put s is equal to infinity, you see that this goes to 0, this goes to 0, this is a constant, and this s, so this is basically ultimately 1 by s plus 2, and in the limit s goes to infinity, this is equal to 0. Now final value, x of infinity. limit s tends to 0 s x of s. So that is limit s tends to 0 s plus 2 by s square plus 2s plus 3. So you put s is equal to 0 here, we get it as 2 by 3. And you can verify this result by taking inverse and finding it out. But it will take much more time. As you can see that if you want to find this function, so this is going to be an oscillatory function similar to what we saw yesterday. So it will come in sines and cos. So it will take some time to rearrange algebraically to make it into a standard form and then find out. But it will be damping. Okay, so it will be some kind of function which will at t equal to 0 we will have 2 by 3 somewhere here. So this is 2 by 3. And then there will be some kind of oscillation. I don't know the details right now, but it will have some oscillation and then it goes to 0. That is why at sorry, not like this. I said the wrong way. So this is a function at infinity it is 2 by 3. Okay. At infinity it is 2 by 3, but initial value is 0. So how does it look like? Initial value is 0. So this is our t. Initial value 0 means it will start from here. It may either go up or down, we don't know. But to know it exactly the form of function, we need to find the inverse, no other way. But all we are saying is the final value. Okay, so if suppose it goes down and then say like this, and then finally it goes to this, something like this. So this will be 2 by 3. So this is what final value is 2 by 3, initial value is 0. So this is our initial value and the final value is far away. Okay, so this is 2 by 3. So this 2-point information, that is initial value and final value, where does it start and where does it end? So that is what we are getting to know. So this is our answer. So that much very minimum information we are able to extract from the given x of s without finding it the inverse. Okay, but I have no guarantee whether the function will look like this way or it could be more likely that it may go like this. I think this is more likely to, that I don't know. Okay, in order to really find out, but I have a feeling that this is what it from my experience. So this is what the function would look like if you find out the inverse. You can check it. So there is some kind of oscillations which will die out and converge to 2 by 3, but initially it is starting from 0, ending at 2 by 3. Any questions?